All right, so this is the quiz that you were taking in class today, 904 Conservation of Energy CFU, and I'm just going to work through it question by question and see how if we can clear up any misconceptions if you were having trouble with them. Starting with question 1, which looks like this and says, pretend the circles on the diagram below are 3 different balls where their size directly correlates to their mass. So in other words, this ball, since it's smaller in size, is also smaller in mass. And then we have ball 2, and there is a third one over here. It says, if all 3 of the masses are rolling along the ground with the same velocity, rank them from greatest to lowest kinetic energy. So the equation for kinetic energy tells us how the different factors affect the amount of kinetic energy that an object possesses, and that equation is 1/2 mass times velocity squared. And so we know that both mass and velocity have an impact on the kinetic energy of an object. In this particular question, it tells us that the velocities are all the same, and thus we're really just looking at how the mass affects kinetic energy. And mass has a directly proportional relationship with kinetic energy, because as that mass gets larger, you will of course have a larger kinetic energy and vice versa. And so the greatest kinetic energy will be the one with the greatest mass, which is going to be ball 2, followed by the medium, and then the lowest. Again, when we look at the sizes, ball 3 is bigger than ball 1, and so it would be the medium amount, and then the lowest kinetic energy would be ball 1, and those should be your answers for that ranking. All right, moving on to question 2. Question 2 says, if an object has a mass of 22.2 kilograms and a kinetic energy of 8,896 joules, then how fast is it going? We're still going to be using this formula because they're giving us a kinetic energy. So they're giving us the amount of Ke as 8,896 joules. They're giving us a mass that is 22.2 kilograms. And they are asking us to solve for how fast, which means they want us to find the velocity. So we're going to substitute these values into this equation, and then we're going to have to rearrange to solve for velocity. So that means it's going to end up being 8,896 equals 1/2 times 22.2 times v squared. And from here you're doing algebra. So you're going to have half of 22.2, which is going to be 11.1. And then that's still going to be equal to 8896. And then again, we're trying to isolate that variable. These are being multiplied, so our next step is to divide both sides by 11.1, leaving us with v squared on the right hand side. And on the left, let's go ahead and put this in the calculator. 8896 divided by 11.1 is equal to that 801.44. It keeps going, but that is v squared. And so again, to solve for v, we will need to take the square root of both sides. So in our calculator, we're going to take the square root of this value, which is 28.31 if we round it to 2 decimal places. Again, make sure that you're rounding correctly when you're doing anything in MyOpenMath. Okay, you'll notice it's the same exact value, but if you're rounding, you need at least 2 decimal places unless the question tells you otherwise. So this one, we're good, and then of course your units will be meters per second. All right, question 3. An object has 200 joules of energy when it is traveling at 6 meters per second. What is its kinetic energy when it's traveling at 12 meters per second? So this can be done in more than one way. We could, if you want to, depending on how comfortable you are with proportional reasoning, could approach it with that. Alternatively, because they tell you that you have 200 joules of kinetic energy, you could plug that into this same Ke equation, because it says it has this much energy when it's traveling at 6 meters per second. And so you could substitute in and figure out what the mass of this object is, and then once you know the mass, you'd be able to go through and solve it a second time with the velocity being 12 and figure out what the energy is. However, you don't have to do it that way. You can, but that's a lot of math. The other way that you can approach this is by using proportional reasoning and just simply looking at what is the relationship between velocity, because that's what they're changing, between velocity and kinetic energy. And when you look at this formula, if you change the velocity, it's going to have an effect on the kinetic energy where if you increase the velocity, say by 2, the kinetic energy would not increase just by 2 times. That's what we're looking at here. Going from 6 to 12 is increasing by a factor of 2. Okay, so we're looking at what happens if I have 2 times the amount of velocity, and it's not going to be 2 times the KE, and it's because of this right here. This is a squared relationship. Okay, and so whatever you do to the velocity, it's going to be squared. So if you have double the velocity, it's going to increase your KE by 2 squared, or 4 times the amount of KE. The original amount of KE in this question is 200 joules. So you're going to have 4 times that amount because you're traveling twice as fast, and the relationship is a squared relationship. 4 times 200 is 800 joules. Again, if you want, you could do this, figure out what the mass is, and then solve for it that way instead. It is entirely up to you. Question 4. We have these pictures again. It says, pretend the circles in the diagram are 3 different balls where their size directly correlates to their mass. So same scenario as before. I can see ball 1 and ball 2. Ball 3 is over here. It's the biggest. And so this is another ranking task. It says, if all 3 of these masses are held at the same height, rank them from greatest to lowest gravitational potential energy. So again, you need to this time be thinking about what is the formula for gravitational potential energy, and what is the relationship between mass and GPE, since the heights are the same. Okay, so the equation for gravitational potential energy is mgh. In this particular question, they're telling you that this is staying the same the whole time. G is, of course, the same. It's 9.8. We're on Earth. And so the only factor that's going to have any impact on the amount of gravitational potential energy is the mass. And so you're going to have the most GPE when you have the most mass, and the opposite is also true. You'll have the least GPE when you have the least mass. Now, ball 3 had the most mass. It was the one off to the side is definitely biggest, followed by ball 2, and then ball 1 is the smallest. So again, that would be the ranking for this particular question. Again, they're randomized, so yours might be in a different order. So just take a look at the sizes, but the biggest one with the biggest mass will also have the biggest GPE. Question 5. A stone is being held at a height of 774 meters and has a mass of 691 kilograms. What is its potential energy due to gravity? Again, we're going to use this formula that we just wrote out here a second ago. And this time they've given us a height and a mass. And so we're just going to substitute in GPE equals the mass it gives us is 691. It does need to be in kilograms. It is, so we don't need to do anything with that. Gravity on Earth is 9.8. And then the height that it's being held is 774 meters. Again, that's already in the appropriate unit. If you were given centimeters or some other unit, you would need to convert, but meters is our standard unit for distance. Kilograms is our standard unit for mass, so nothing else is required here. We just plug those numbers in, and now we have a multiplication problem. 691 times 9.8 times 774 is what goes into your calculator, and when it does, you're going to get this value. You do need to type this entire value in. Because again, the default here for MyOpenMath is 2 decimal places. Now this one's 0.2, so technically 0.20. It's not spitting out the extra digit because it's not there. But if you're using an Inspire and you have it reported in scientific notation, this might present a problem because it might be telling you 5.241 times 10 to the 6th power. So you might have 5.241 e 6. I think that's what I said. And that's going to be counted wrong. Because if you do that, that's the same as rounding this to 5,241,000. You have lost all of these digits and all of this precision. So be very careful if you are using the Inspire, and you might need to double check your settings to make sure that it's not chopping off decimal places or giving you scientific notation when you don't want it. Now you could put this in scientific notation, you would just need to include all those digits. All right, so I'm just going to type it out as is. If you use the Desmos built-in calculator, you could copy paste it, but 5,241,373.2. Type it exactly as it is, and then energy is in units of joules. And did I type it wrong? I did. See, this is what happens. If you're not careful, and I missed a digit, and you type it in wrong, it'll do that. All right, because this is a CFU, if you type it in wrong, it's not going to give you credit. So be careful whenever you're doing that, so that you don't make a mistake like this, because you're not going to get credit on it if you do that. All right, question 6. If an object has 430 joules of potential energy when it is 20 meters off the ground, what is its potential energy when it is 80 meters off the ground? Again, this is kind of similar to that other one where you have a couple of different methods for solving this. Because they tell you the amount of gravitational potential energy when it is at a specific height, you could use that information. 430 joules equals m times 9.8 times the height, and this first one was 20. You could use that information to solve for mass, and then once you know the mass, you could then plug it back in with this other height of 80 meters and have that mass times 9.8 times 80 and figure out what you get. But you don't have to. Again, that takes a couple of steps. All this is a proportional reasoning problem. They're telling you it was 20 meters off the ground and now it's 80. And so what they have done is they have increased the height by a factor of 4. So the height is now 4 times more. And so that's the question. If you increase height by a factor of 4, what happens to gravitational potential energy? And height and GPE have a directly proportional relationship. So when you have 4 times the height, you should have 4 times the GPE. And the question tells you that you started out with 430 joules of potential energy. So you just need to multiply that number by 4. So 430 times 4 will give you the amount of gravitational potential energy that you have when you quadruple the height. And it would be 1,720 joules, because that is 4 times as much. And again, your unit is still the joule. Question 7. The table below shows the length of 2 springs when stretched by a force. Which one has a greater spring constant or stiffness? Again, when we look at elastic potential energy, the equation that we use for elastic potential energy for EPE is this one. EPE equals 1/2 kx squared. And in that formula, the spring constant is this K. It represents how stiff or how loose a spring is, and it tells you in newtons per meter how much force it takes to stretch it by 1 meter. You could have newtons per centimeter, in which case it's the force to stretch it a centimeter, which is kind of what this table is giving us, is the force per centimeters. But it's still going to represent how loose or tight a spring is. And so the larger this number is for K, the more force it takes to stretch it, which makes it a stiffer spring. And so if you look at this, the length of these springs, initially when there's no force, they're not the same length. Spring 1 starts out at 17 centimeters, whereas spring 2 starts out at 10 centimeters. However, as you add force to them, maybe you're adding weights to the end and letting them hang and get longer, whatever, but as you add that, it's going to cause the spring to stretch. And so you're looking at which one is going to stretch the most. Now, if you're adding the same amount of force, okay, then, and they have the same spring constant, then you would expect them to stretch by the same amount. And that's not what we're seeing here. Okay, now yes, they have different lengths, but what you're looking at is the difference. So like with 0.05 newtons, or maybe we'll go up to a larger amount, like it doesn't matter, pick one. But at 0.1 newtons, your first spring started out at 17 and now it's 18.1. Your second spring started out at 10 and now it's 13.8. And so this one only stretched by 1.1 centimeter, whereas this one stretched by 3.8, which means this one's easier to stretch when you put the same amount of force onto it. If you're looking for the stiffer spring, it's the one that's harder to stretch, which means this one should be harder to stretch because it's more resistant to changing length, is how it's worded here. But spring 1, because it is more resistant to changing length, means it's more difficult to get it to stretch. And again, all you're looking at is comparing how long the spring is before you stretch it, before any force is added, with how long it is when the same amount of force. So pick a line, it doesn't matter, I just chose this one. But then you can see how much each one stretched by. This one went from 17 to 18.1, this one went to from 10 to 13.8. All right, question 8. The graph below shows the force required to change the length of a spring. What is the spring constant according to this data? All right, let me make this full screen for a second so we can see this graph. Okay, so this is the displacement of the spring because it's showing the change in length and the force. If you have a force displacement graph, the slope of your graph is your spring constant, which means we just need to find the slope of this graph. It's kind of difficult. You need to find a spot where you can cross a grid line, like right here is a good point to use because it's on the lines to find the slope. And I can use the origin as another point. And so this point would be at an x value of 0.5 meters and at a y value, if you follow this over, of 8 newtons, and then another point would be 0 and 0. Okay, and so if you want to find the slope, again, these are the 2 points that we chose. Okay, but if you want to find the slope, it's change in y over change in x, or rise over run. Again, going from 0 to 8 for my y value, my change in y would be equal to 8 newtons. If I went from 0 to 8, my change in x would be going from 0 to 0.5. Okay, and so then you would just do change in y over change in x, rise over run. 8 divided by 0.5, or 8 divided by half is the same thing as 8 times 2, should be 16. And it will be in units of newtons per meter because, again, those are the units that we have on the graph. Oops, I didn't answer it, but yes, same thing. Okay, moving on to question 9. This one says, a boy pulls back on the slingshot band, displacing it 0.079 meters from its resting length. If the spring constant of the slingshot band is 923 newtons per meter, what is the velocity of a 0.0 kilogram rock when it's launched? So, again, this is looking at the elastic potential energy equation. Again, the formula for that is EPE equals 1/2 kx squared. Okay, and this time though, they're not actually looking for any of this stuff. Instead, they want to know how fast it's going to go afterward, which means that the elastic potential energy that is initially possessed by the slingshot is going to convert into a different type of energy, specifically kinetic energy. And again, what we normally do when we're approaching these problems is we write an energy transfer equation, but if you didn't know that, then you can just look at the information that's given. You have a displacement, you have a spring constant. You should know right off the bat you're going to need this. And then you're being asked for velocity. You should know right off the bat you're going to need this. So the motion that it ends up with is due to the elastic potential energy that it starts with, and that's how you write your equation. The EPE that it starts with initially will be equal to the KE that it ends with at the final state. And again, you're not going to leave it like that. You're going to go and put these equations in there. So you're going to have 1/2 kx squared equals 1/2 mv squared, and then you're going to start to plug in numbers. Now, if there were other forms of energy present, like if it said that they were launching this thing up at an angle or something, you might have to have GPE over here, but they'd have to give you that. They'd have to give you some information about that, and they don't. Okay, it would be better if they told us specifically that it's being launched horizontally. That would make the question a little bit more clear, but they don't tell us anything about it being launched any other way, so we're going to make the assumption. And we're going to plug in. So the K value for this is 923 newtons per meter. The X value is 0.079, and that value is squared per the equation. And that is equal to 1/2. And then this time the mass is going to be the mass of the rock, 0.06 v squared. So that is your equation. Solve the entire left-hand side. Let's see what we get. 1/2 of 923 times 0.079 squared is this, 2.88, that's rounded, equals half of that is 0.03 v squared. And then we're going to divide both sides by 0.03. to get v squared equals 96.01, and then take the square root to get v is 9.80. It's actually 9.798, but when that rounds that up, that rounds that to from 79 to 80 meters per second. There you go. This is question number 10. Question number 10 says, assume the roller coaster below is frictionless. At which of the following points on the roller coaster above is the kinetic energy greatest? First things first, this word frictionless right here tells us that we are going to make an assumption that there are no external forces acting on our roller coaster, and thus we're going to have conservation of mechanical energy. So while the kinetic energy is not going to stay the same because this ball is going to speed up as it goes down, it's going to slow down as it rises, whatever. The speed won't stay the same, and thus neither will the kinetic energy. So although that's not staying the same, the total amount of mechanical energy is. We're going to see a conversion from gravitational potential energy at these greater heights, like the start, to kinetic energy as it goes downhill with the same total the whole time. So up here, maybe it's all gravitational. As it rolls down, think of those pie charts from class. A small piece of kinetic energy shows up. Most of your pie is still gravitational, and then as it continues rolling down and loses height, more and more and more of your pie is kinetic energy because less and less is gravitational. Again, remember that GPE equation. GPE is mass times gravity times height, and so as you lose height, as this number gets smaller, you're going to have less GPE, which means you're going to have more kinetic energy to replace it because the same total needs to remain the same. So where is the kinetic energy greatest? That's going to happen at the point where the GPE is least, where the height is lowest, which would be either 0.3 or 6. I do have a choice for 0.6 on this one. These are randomized. Sometimes it's not a choice. Pick your lowest point for your diagram. On mine, that's 0.6. Follow-up question, where is the total mechanical energy greatest? And this is that trick question, because if it's frictionless, we just said that we're going to assume total mechanical energy remains the same, which means it's the same everywhere. Next question. A horizontal force of 44 newtons is applied to pull a 4 kilogram box initially at rest, a horizontal distance of 10 meters. The box's final velocity is 10 meters per second. How much energy was used to overcome friction? Guys, when you see this question, how much energy was used to overcome friction, it is implying that there's probably friction. However, it is possible the answer could be 0. This is the same thing that they're asking. It could be worded in different ways. How much energy was used to overcome friction is the same thing as if you see a question that says how much energy is dissipated by friction or how much energy is lost due to friction. You might even have a question that just says, is there friction? Or you might see how much work is done by friction. All of those require you to approach this question in the same way. So let's go ahead and talk about how we approach it. So I know that I have this box, and it is initially at rest, so its velocity is 0. And then I know that over here, it's moving. It is moving with a velocity of 10 meters per second. Okay, and so the question is, why is it moving over here? Because this initial state didn't have any motion. So where did that motion come from? And again, this is where we typically would write our energy transfer equation. I don't have any initial energy, 0. And yet at the end, I obviously have KE. Okay, so where does that KE come from? It's definitely not equal to 0. Well, it comes from the work that was done, that pull that was applied to the box. Okay, if you see a push or a pull, that's work. So the work that we did is what gave us the KE that we have at the end. And the thing is, these might not be equal. I know I wrote an equal sign right here. I'll talk about that in a minute. They might not be equal to each other. Okay, so let's figure out how we can address this or how we can approach this. I'm going to go ahead and start by substituting in the variables because I don't know work, but I know work is force times distance. Okay, and then the KE equation. We're going to set it equal to the KE equation, which is 1/2 mv squared. And again, I want to see if these are equal because they might not be. If they are equal, then the answer to the question, how much energy is used to overcome friction, that answer would be 0. But if they're not equal, then we need to figure out what's going on. And that means that friction is present and we can figure out how much energy is lost because of it. Again, let's go ahead and plug in some numbers. Force times distance, my force here is 44. My distance over which my force is applied is 10 meters. 1/2, the mass of this object is 4 kilograms, and the velocity that it's moving is 10. And so this is going to be 440 equals, this is 2 times 10 squared, so 2 times 100 is 200. So right off the bat, guys, these are not equal to each other. I just wrote this ridiculous statement. 440 does not equal 200, not equal. Okay, so why aren't they equal? Well, there's friction. That's the whole point. It's not moving as fast as it should be. So how much energy was used to overcome friction? We did this way in class a couple times where we just figured out, hey, here's what we started with, hey, here's what we ended with. They're not the same, find the difference. And that's basically what we need to do now. But we could also have written it out into our equation. We could have had our 440, or if you go back here, our work, plus the work done by friction equals our KE, 200. And we could solve for work done by friction. Or we could have written the equation like this. Our 440 joules of work equals our 200 joules of kinetic energy plus whatever energy got dissipated. Those were the two different ways that we did this in class. And if you write it one of these two ways, you're going to end up doing the same thing that we just said. We're going to end up subtracting. Because if I want to solve for this, I have to subtract 440 from both sides. If I want to solve for this, I have to subtract 200 from both sides. And the only difference in the answers I'm going to get with these two approaches is the sign. This one is going to give me positive 240. This one's going to give me negative 240. And that's because this one is solving for the work done by friction, and this one is solving for dissipated energy, but it's the same magnitude. The answer is the same. And so if I wanted to answer how much energy was used to overcome friction, I would report it as a positive number, 240 joules. If instead this question had said, what is the work done by friction? The only difference would be putting a negative sign in front of this number. So you're welcome to answer it either of these ways, or just solve them independently and then figure out what to do with it. It's the same thing. You're going to end up subtracting. Check your sign at the end. Depending on how they ask the question, you might need to put a negative in front, and that's only going to be if the question specifically says what is the work done by friction. Otherwise, leave it positive. Or rather, just provide the magnitude. It's not really positive. Okay, let's look at the next question. Question 12. says the bar graphs represent the kinetic energy, Ke, gravitational potential energy, Pe. Please note that they are only using these letters to represent GPE, Pe, that's what's in the graph. And elastic potential energy, EE. That's not the thing we normally use, but that's okay. We normally have EPE, but they're telling you to match that. Which graph might represent the pole vaulter at the peak height of her vault? So if you don't know what a pole vaulter is, that might make this question a little bit tricky. So let's take a look. This is a pole vaulter. Okay, they run and they stick this pole into the ground, and then they use it to launch themselves over a bar like this. When they first stick that pole into the ground, it bends quite a bit actually. Let me find a different picture so that I can show you that. Okay, but that pole will bend. Here. There it is. All right, here is a different image. It will bend as they launch themselves upward. And as it bends like this, when you have deformation, that's when you have elastic potential energy, where it's trying to return to its normal shape. Okay, now it's not asking about that point, it's asking about her peak height. That guy wasn't at his peak height yet, she is. Okay, at her peak height, this pole is no longer bent, which means we do not have elastic potential energy at the peak height. Okay, if you look at these, the only one that doesn't have that is B. You only have elastic potential energy when you have stretching, compressing, or deformation of your object. If it's a straight post like this, it's no longer there. Okay, it has to be deformed and trying to return back to its normal shape. At the peak height, we should also expect to see a lot of potential energy. So my PE bar should be really high, which is what I see in B as well. And then lastly, she should be moving. You should have kinetic energy up there. She has to go over that post. So again, that again reinforces that we are looking at bar graph B. All right, question 13. A 109 kilogram skier starts from rest at the top of a 63.5 meter hill and skis into the valley below. I'm going to start drawing a picture for this because it's going to be helpful. So we have this scenario. It talks about starting on top of a hill, going into a valley, and up a second hill. Okay, it tells us that they start at rest up here. It asks us rather how fast they're going over here. And it tells us the heights. It says that this first hill has a height of 53.5 meters, and that this second hill is shorter. It has a height of 36.9 meters. Okay, and that's the question. How fast would you be moving here? Let me move this over so the whole picture's on the screen. Okay. So it also tells us assuming no friction. So we are going to assume conservation of energy, that the total amount of energy here equals the total amount of energy here. Do I care about down here? Not really. Could I find how fast they're going down here? Sure. Do I need to? No. If energy is conserved, I can pick any points. I can set this point equal to this point, even though this point's in between. Doesn't matter. I could also solve for that point, or whatever point. But we are going to use this one and this one because that's the easiest one. And so that's what I would recommend you doing. Instead of trying to find something random down here, which we don't need, set that equal to that. And so what forms of energy are present up here? Well, I know it's not kinetic, it's not moving, but I do know that I have height. So I have GPE initially at the top, and that's it. And we're going to set that equal to the energy at the end. And I still have height, so I have GPE at the end. But I also should have some velocity at the end. I have to because I'm not as high as I was, so that some of that will be kinetic. So KE final. And again, I don't know the energies. I know masses and heights, and so that's what we need to do is go and plug in mgh for GPE equals mgh plus 1/2 mv squared. All right, so from here, little trick. If you have the same variable in every term, it has to be in all of them. Mass, mass, mass. Cancel it out. Do you have to? No, you're welcome to leave it in there, but it does make your math harder. It's an extra step. You can't do this, by the way, if your equation has EPE in it, because that equation doesn't have mass. 1/2 kx squared, no mass. You can't do this if you have work. Force times distance, there's no mass. So only if you have that variable in all of your terms, which I did. So I'm going to go ahead and cross it off. If you want to leave it in, you go right ahead. You're going to get the exact same answer at the end. G is 9.8. The height initially is 53.5. I'm going to set it equal to G is 9.8 times my second height, 36.9, plus 1/2 V squared. And that's what we're looking for, is that V. So let's go ahead and solve the left-hand side of the equation. 9.8 times 53.5, and that is 524.3. And then set that equal to 9.8 times 36.9, which is 361.62, plus 1/2 is 0.5. If you'd rather write it that way, it doesn't really matter, V squared. Please don't add these. These are not like terms. This one has a V squared, this one doesn't. Instead, subtract 361.62 from both sides. And that will give you, on the left-hand side, 162.68. which will be equal to 1/2 V squared. Again, you're trying to get this by itself, so you need to divide both sides by 1/2. Dividing by 1/2 is the same thing, by the way, as multiplying by 2, if you'd rather write it that way. But that's 325.36 equals V squared. And then you just have to take the square root, because you don't want V squared, you want V, and V will be the square root of that value, which ends up being that number. And let's see. There it is, same thing. All right, follow-up question. If friction were present, which of the following statements must be true? The skier system is a closed system. That is not going to be true. A closed system is one in which your energy all stays in the system. There's no exchange of energy or loss of energy with the surroundings. There's no work being done. That is clearly not what would be the case. If there were friction, there would be work being done. We would expect energy to leave our system or to be dissipated from our system. That is the definition of an open system, not a closed. Friction will do positive work on the skier. Nope, friction only does negative work. All it does is remove energy, not add it. So don't check that either. Total mechanical energy of the skier will be conserved. No, it will not. That's the whole point. It's an open system. When friction's present, there's an external force doing work, causing your total mechanical energy to decrease. The skier won't make it to the top of the second hill. That could be true, but it doesn't have to be true. Depends on how much friction there is, so we're not going to pick that. The skier's speed at the top of the second hill will be slower. That is absolutely true. If the skier makes it to the top of the second hill, they would be moving slower. And then total mechanical energy is conserved. That is not going to be true. It's just that one. All right, last question. A baseball speeds up as it falls from rest toward the floor. How do the kinetic and gravitational potential energy of the ball change as it falls, and why? Again, as something falls, you're going to expect an exchange from gravitational potential energy to kinetic energy, just like here, from gravitational to kinetic as it goes down. Okay, same thing if it's in free fall, same thing if it's a pendulum, it doesn't matter. Okay, if you're losing height, then you're going to expect it to be converted into kinetic energy, unless, of course, you're losing height as you compress a spring or something. Okay, but otherwise, a falling object is going to get faster. So we're going to pick the one that says that the gravitational potential energy decreases and kinetic energy increases. Which is this right here. KE increases while GPE decreases, because GPE is transformed into KE. That is absolutely correct. Last question. If air resistance is considered during the fall, how does the kinetic energy just before impact compare to the gravitational potential energy when it's dropped? Guys, if you have air resistance or friction or anything that's causing your system to dissipate energy, then you're going to end up with less energy than you started with. So your initial amount of energy, whatever form it is, in this case it's gravitational potential, but the initial will be greater than the final if you have air resistance or friction, and that's what this first one says. All All right, guys, that is it. If you had trouble with this quiz, I would strongly encourage you to do the unit summary for extra practice. It's also a daily grade redo and could replace your quiz grade. But if you're having trouble with it, you need to make sure you review before we take the unit quiz and the unit test in a week and a half.